Yeah, comes on everyone. Let's start off. Hope everyone has started solving semiconductors PYQs. Last thing that we did, we are doing about magnets. So let's go ahead with this. The last thing that we did was this BH and angle of dip. Next one is vibrational magnetometer. Quite an important one in entire magnetism, right? Half of the times whenever they ask questions, it is based on this thing. Vibrational magnetometer. It's an important one and not difficult. So suspend a magnet. So if you take a magnet and if you suspend it in air, North Pole, South Pole. So this will have some magnetic momentum. And what will happen if you just suspend the magnet in the air, it will align in the direction of the Earth ka magnetic field. Because if you remember, torque is equal to mu cross B, it will align in the direction of the magnetic field. So if you look at this top view, this is your magnetic field and this is your BH. Now if you displace this by theta, then your magnet becomes like this. This is your magnetic moment. This is your horizontal component BH. Then we get torque is equal to M cross BH, which is MB sine theta. And torque is equal to minus I alpha. And this becomes MBH theta. This is for small theta, sine theta becomes theta. This becomes an SHM. So alpha is equal to minus MBH by I theta. Therefore, the time period T is given by 2 pi root over I by MBH. That should definitely mug up the formula there. If you suspend a magnet and if you oscillate for small oscillations, it will do an angular SHM. Where here I is the moment of inertia of the magnet, M is the magnetic moment, and BH is the Earth's magnetic field. That's it. Concept-wise, it's not a big concept or anything. It's just an SHM there. So how are the questions framed on this? So let's see. I'll show you how the questions are framed on this. Important one. Most of the questions on magnetism were on this. All clear with this? And if you see the same thing we did in dipole also. Torque is equal to P cross E. Small oscillations, we got something similar, I by PE. This was a JE question. So there were two magnets. North, south, M1, M2, both are in the same direction. The time period is T1. In the second case, you kept both the magnets opposite to each other. North, south, south, north. This is M1 and this is M2. Time period is T2. Find M1 by M2. Get this, I'll give you a minute. Again, what is the formula? 2 pi root over I by mbh. BH is the earth ka horizontal component of magnetic field. M is the net magnetic moment. So let's see the formula. So T1 will be 2 pi root over, remember, moment of inertia will add up. Now, I don't know the moment of inertia, so I'll take I1 plus I2. Since it didn't say they're identical magnets, we have no idea. What about the magnetic moment? Since both are in the same direction, it will be M1 plus M2 into BH. Moment of inertia is kind of behave like scalar, so it doesn't matter how you align them. So moment of inertia will add up, whereas the magnetic moments will subtract. Again, we are assuming M1 is greater than M2, so we take the magnitudes anyway. And then you're done. So substitute here, T1 by T2 will be root over M1 by M2 by M1 plus M2. Square root of both the sides and then cross multiply and finish it off. You'll get M1 by M2 by ratio. I'll leave it there. Clear? Easy question, but you should know the formula. Because in the exam, the question will be like this. In a vibrational magnetometer, two magnets are placed in the same alignment, and in the second case, they're kept in the opposite direction. The time periods are T1 and T2. Find the ratio of M1 by M2. That's it. They won't even give you the picture and all like this. The whole question will be in a sentence. And first of all, you don't remember the word vibrational magnetometer, there only you have to use blows off. Clear with this? And the question is straightforward. You should know how the setup looks like. So that's it. There is nothing more than this in this question. So be careful with the terminology. Next thing. Now, last class I showed you how to find the magnetic field when the points are very far. We compared it with the electric dipole. But what if the points are much closer to the magnet? What if the distance is not far? So this is another case there. So magnetic field on the axial line. Now these formulas now, even I don't remember them. So whenever they come, I derive. It is not difficult to derive. So listen to the derivation for that purpose. If at all the question comes, if you know how to derive, you can derive this in less than a minute. So North Pole, South Pole, let's say there's the point P here. This distance is R. So generally what we do, we always take the R to be large, but not necessary. Sometimes if R is comparable, then this distance be L and this distance be L. So how do we handle this? Magnetostatics. This North Pole is small plus M, South Pole is minus M. M is your pole strength. Capital M is M into 12. So the logic is this. We're going to use this plus M and minus M. So at a point P, do you guys remember how to find the magnetic field? KQ by R square. What is K? Mu naught by 4 pi. What is Q ka place mein? Small m. What is the distance? R square. Isn't this the formula? So basically, I'll treat them as 2-point charges and I'll find the magnetic field at point P. So the magnetic field at point P, the plus m will give you a field mu naught by 4 pi. Small m, what is the distance? R minus L whole square. R is the distance from the center of the magnet. What about the negative one? Mu naught by 4 pi. M, the distance is R plus L whole square. Now we are getting why the distance is taken as 12. Because of this. नहीं तो यहाँ पे L by 2 आएगा, it will look dirty. So now you're done basically. Take out mu naught m by 4 pi common. The numerator will become 4RL, denominator will become R square minus L square whole square. But what is m into 2L? That will become 2 mu naught by 4 pi capital M by R square minus L square whole square. There, that's your formula. So B on the axial line is 2 mu naught by 4 pi capital M. I think I missed an R here. MR by R square minus L square whole square. Now it's difficult to remember this. At least I can't remember, so I derive this every time. But it is important because they can ask questions like this. Now, see, if R is much greater than L, then your B ka value becomes 2 mu naught M by 4 pi M by R cube. Isn't this your regular formula? So this is proportional to 1 by R cube. If that R minus L tends to 0, means the points are very close to the pole, the denominator becomes almost constant. A huge value becomes R power 1. This is important, right? This, I have seen questions being asked on this. When you are far from the magnet, how does the field vary? 1 by R power 1, R square, R cube. When you're very close to the poles, how does the field vary? Linear function, R power 1. Those will be the theoretical questions. So when a point is moving very close to the poles, the field varies linearly. Near the poles, field varies linearly. From far away from the poles, the field varies as 1 by R cube function. Those will be the theoretical questions. Clear with this? And how do you know you have to use this formula and not the far off formula? You will see the values. Any doubts on this page? Understood how I derived this? The derivation is important because remembering the formula, I don't think so. But it just looks like magnetism. The question would be there. Now, if you look at this, a bar magnet of 0.1 meter long. So he gave 12 is 0.1. Distance of 20 centimeters. So he gave R is equal to 0.2 meters. Can you see? R and L are comparable. That is a catch. So if they're comparable, don't use that far off formula. And unfortunately, that also will be there in the answer. So it's a trap. You have to be careful. Clear with this? If they had said R is equal to 3 meters and L is equal to 0.1 meters, you could have ignored it. So using the same logic, if I try to find the field on the equatorial line, North Pole, South Pole, there's a P here, let this distance be R. This is L and this is L. Same story. I can treat this thing as plus Q charge, this thing as minus Q charge. So this will give the field this way, and this will give the field this way. It will be horizontal. Can you find the field at point P? Try. Just to give a reference, this thing would look like this. It's like having a plus Q charge and a minus Q charge. We have done these kind of questions in electrostatics. If you have a point P, this plus Q is pushing the field away and the minus is attracting the field this way. The net resultant will be this way. Instead of Q, you have to use small m. Try, I'll give you a minute. Calculate the magnetic field at point P. So if they're going to ask a question when it is very far, when the distances are comparable, they will stick to equatorial and axial line. They will not give any random angles. If they give you angle, generally it is always when the point is very far. Let's see. Right behind ये सब जाएगा. So plus m minus m. This is point P. This is distance r. This is L. So this is root over r square plus L square. Take this angle to be theta. This is B. This guy also will be B. This will be theta. This also will be theta. Symmetry basically. This is your net horizontal to be cos theta. So B ka value will be mu naught by 4 pi. That is your K Q by r square, which is r square plus L square. So the magnetic field at point P will be 2b cos theta 2 mu naught by 4 pi m by r square plus L square. Cos theta is L by root over r square plus L square. 2ml will become capital M. Mu naught by 4 pi capital M. So answer should be always given in capital M, because they'll not give you pole strength. They will give you generally the magnetic moment. L square whole power 3 by 2. There. That's your magnetic. You can see the formula changed completely. If R is much, much greater than L, then your magnetic field becomes mu naught by 4 pi m by r cube. As expected, you got the formula. So this is actually this will cover everything. If your R tends to 0, you will notice B becomes almost constant. This is another good point. That means if you're moving around the center of the magnet, you will observe the field is almost constant. They'll ask this kind of a question. On the equatorial line, very close to the magnet, how does the field vary? R power 0. At the poles, if you're very close to the poles, how does the field vary? R power 1. On the axial line, if you're very far, on the equatorial line, if you're very far, how does the field vary? 1 by r cube. Clear with this? How does the force between two dipoles vary? 1 by r power 4. So these are important, these powers and all that stuff. Clear with this? Another way of asking questions on magnets. They will say a bar magnet is placed along the north and south pole of the earth. Now see, in mains mein, this entire chapter might give you one question, but don't think like that. You will be writing two mains, two bits, CET, Vellore, Manipal, UG, Advanced, almost 8 to 9 exams. If you take all the 9 exams, in magnetism, you'll at least find 5 to 6 questions. Getting it? So think in that perspective. That is the reason I'm telling you, finish your PYQs by next week. At least these main chapters. Because these chapters now, what I'm teaching you today, if you don't revise this by tomorrow, trust me, day after tomorrow, you half of the things will look like pretty hazy. Why all that? If I ask you a few questions now, you will start struggling already. Anyone remembers what is avalanche breakdown? When does it happen? What doping? Now, if you remember, it is fine. No need to answer. I'm just asking. Right? In a photo sensor, in a photodiode, it works in what bias? Solar cell will work on what bias? The width of the depletion layer depends on what? If you have high doping concentration, will the width be bigger or smaller? Xenodiode is used as what? Voltage regulator. In a bridge wave rectifier, what is the frequency of the output? समझ में आ रहा है? The words का thing. In a p-type semiconductor, right? What kind of impurities are added? p-type trivalent atoms, holes होना चाहिए. n-type में pentavalent, extra electrons होना चाहिए. In a p-n junction, what is the charge of p-type? In a p-n junction, charge of p-type is negative. Only p-type is neutral. What is law of mass action? समझ में आ रहा है? So you will forget these things. You have to solve. Ne into NH is equal to Ni square, where Na is the intrinsic concentration, which is 80 power 3 by 2 e power minus delta Eg by 2 kT. वो important नहीं है, but you should know it depends on temperature. If you increase the temperature, there will be more Ni will increase. You get more conductivity. Getting these things? What is a conduction band? I can keep asking you. When we need chota terminologies, they'll play around like this. So please make sure to go through this. I'll be conducting 2-3 exams also in all these chapters. So I had a very bad experience with these chapters like 3-4 years back. Normally what used to happen now, we used to kind of, I used to finish it off and used to leave it. मतलब advance में नहीं है करके, we used to ignore this. And then I think 2019 कोविड का पहले, somewhere I don't remember, but long back, 4-5 years के ऊपर हो गया था. 1 year what happened, there was a kid, उसका एडवांस नहीं आया, बट मेंस में ना he lost a seat in NIT Nagpur because of around 5 marks. Getting it? He was getting NIT Nagpur में mechanical or something. 5 marks में he lost that. मतलब 5 marks आ गया तो he would have got that rank and he would have made it. And that year in the mains paper, right, there were 3 questions on all these mains ka topics. And the questions were so hopeless. मतलब seriously hopeless. One question was like this only. There is a diode, there is a resistor, there is a battery. Find the current in the circuit. Which we did. And this guy saw the question, didn't even remember anything, forgot and left it and came. 3 questions made, 2 questions were so hopeless. Matlab, if you had just read the notes, you would have got it. 2 questions would have been how many marks? 8 marks. He would have got into NIT. Now, I felt bad. Matlab, chalo, he didn't score and all, but then I thought like, yeah, maybe if I had pushed him a little more, na, that 8 marks, right, would put him in a decent college. He joined in local Mumbai college somewhere, some Todmal college, aisa kuch to tha. I don't remember the name. It starts with some T. Decent college in Mumbai, but NIT Nagpur is better, right? वहीं पे तवड़माल में जाके मैकेनिकल लिया वो NIT नागपुर मैकेनिकल. So then I said, yeah, no, yeah, we should not ignore these chapters, even that is not there for advance. So that is the reason I keep pushing you and I keep telling you. Because these chapters before COVID, so we always used to ignore, like we never cared about these things. But game is not that anymore. No, why to deprive you of at least a decent college? क्या पता, कुछ भी हो सकता है. So see, this was the question. So we kept a magnet like this north and south. So this was north, this was east, this was west, and this was south. And last class I told you, remember, BH ka value goes from where to where? Earth ka magnetic field goes from south to north. That means if you keep this magnet in this kind of a magnetic field, the magnet ka magnetic field and Earth ka magnetic field will cancel, na? So they'll give 4 options like this. Where will the null point occur? North of the magnet, south of the magnet, east of the magnet, west of the magnet. बस ऐसा होगा question. They'll give four options A, B, C, D, and they'll ask you where is the null point. In the second case, you keep the magnet in the reverse. South, north. Where is the null point? Where is the null point? Draw the magnetic fields, you'll understand. Now, if you look at the magnet ka thing, the magnetic field lines will emerge out of the north pole and they make a turn and come toward the south pole. Now, look at this here. So, at this point here, the BH and the Earth ka magnetic field are opposite. So, the null points will occur on the equatorial line. And there are more magnetic fields. I'm just not drawing them. What about this guy? Here, the magnetic field lines will come from the north pole and they go here. Now, here, if you see, the magnetic fields actually add up here. So, equatorial line mate won't become zero anymore. Here, they will cancel on the axial line. Did you see how the answer changed just by the orientation? That simple thing, but you should know. Got this. So BH cancels out magnetic field due to the magnet. You get questions of this sort. Clear? Next thing, the second most important thing in this chapter. The first important was a vibrational magnetometer. This magnetic field was okay. The second important thing is a moving coil galvanometer. Now, this is also there for your boards, even if you're in HSE or CBSE. Now, if you remember, we did this thing, ammeter, voltmeter, how to convert and everything. We did this thing in current electricity instruments. Right? But how does this exactly work? What is the construction and working of it? So let's see the picture first of all. This is the top view. Let me show you the side view also, then I'll explain you the parts. This is the side view. Now look at the parts here. First of all, if you see, we have two magnets here, North Pole and the South Pole. And if you look at the magnets, they're a little weird. They're not flat. They're actually curved here. Okay. And this gray thing in the middle is the cylinder. This is the top view. If you actually see the side view, this is the cylinder. That is a cylinder. And this here is your coil. This green things which I'm marking is a coil. So basically you take a current carrying coil and you wind it, around the cylinder. So it looks like this. So the catch is this. Whenever you send the current through this green color coil, it will have a magnetic moment mu bar. And this magnetic B bar will create a torque. Because of this torque, the cylinder will start rotating. If the cylinder rotates, and if you see here clearly, they kept a needle. You can see there is a needle pointing here. This needle will start rotating. The more current you send, more the needle will deflect. So we are going to find the relation between the needle deflection and the current. You're getting the concept there? When you send the current through this green color coil, it will produce a magnetic moment. In the presence of a magnetic field mu cross B, you get a torque. This torque will try to rotate the cylinder, and you actually try to resist this cylinder by this springs here. There is a lower suspension spring and an upper spring here. These will try to oppose the rotation. The more current you send, more the needle will rotate. So first of all, let's understand why is the shape that curved. If you look at the magnets here, the poles are not straight. North pole, south pole. If you look at the cylinder here, you will notice something here. These field lines are perpendicular. This cylinder has a coil. So it is deliberately made that way. It has a purpose. So these poles are cylindrical in shape, because of which the field lines will enter the cylinder perpendicular to the surface. The field lines will be always radial. Poles are cylindrical. Therefore, the magnetic field lines are radial. You will see what is the advantage of that. That is, this B bar is always parallel to the coil, and perpendicular to the area vector. So what happens? So what happens? Now, if you look at the side view, this was the cylinder. This cylinder is connected with a spring on the top and the spring at the bottom. So these springs, right, will resist the rotation. So K is torsional constant. Anyone remember what is torsional constant? We saw this 2 times so far. Where did we see these things? First time we saw in elasticity, rigidity modulus. When you twist a cylinder, torsional constant will give you the opposition to the twisting. कौन सा chapter में था वो? Elasticity. Anyone remember the formula by any chance? Rigidity modulus eta pi r power 4 by 12. It is a power 4 आएगा वहीं पे. This question say, twisting a cylinder, find the torque required to twist the cylinder. Pi eta r power 4 by 12. That is your torsional constant. The second time you saw this thing was in SHM. Torsional pendulum. याद है? If you twist this thing, the pendulum will rotate. So torsional, torso, it is your twisting rotation or twisting torque. So we have 2 springs like this. So these things will try to resist the rotation of this. And now we have our coil here. So this coil will generate a magnetic moment, mu bar. And the magnetic field is always perpendicular to this. So what is the advantage? Think about this. If you send the current through the coil, won't the coil start rotating? If the coil rotates, normally what would have happened if you kept B constant? What would have happened? The theta would have changed. Means you will get different torques for different rotations. But now, luckily, mu cross B, your torque is constant. It doesn't matter how much it rotates. Mu B sine 90, this is a constant torque. So independent of rotation. So this is your magnetic torque. So we get torque magnetic is equal to torque torsional torque, the twisting torque in equilibrium. This will be mu B, which is NIAB, and torsional torque is K theta. There we get theta is equal to NAB by K into I. Theta is proportional to I. So the more current you send, the more the angle will deflected. So for 1 ampere, if you deflect 10 degrees, for 2 amperes, you deflect 20 degrees. That is how your galvanometer works. So when you send a current through the galvanometer, IG, if you remember, that is how the galvanometer knows what is the current. Clear with this? Working is clear, straightforward, but when you write in boards, you have to write a lot of stories there. Just to put the whole thing in a more beautiful theory there, I'll send you some reading material on this, so make sure to read it. This was the whole theory there. So if you see a few statements, the torque is NIAB, right? The pole pieces are made cylindrical. As a result, the magnetic field at the arms of the coil remains parallel to the plane everywhere as the coil rotates. Quite an important thing. And then we have the deflection of the coil is theta, then the torsional constant of the suspension is k theta. You end up with this formula there. And quite an important thing. I is equal to this thing. I wrote theta, here it is I. So here there's one more important thing. This quantity K by NAB is called as galvanometer constant. There is a question like this. Find the galvanometer constant. There is also another name for it. It's also called as figure of merit. It did come once, like they said find figure of merit and people were like clueless, what the hell. It's also called as figure of merit. It is simply the current per unit angle. They'll give you all the values. They'll give you K, N, A, B, and they'll ask you figure of merit. The story was pretty straightforward though. You send the current, you get a mu bar, which is NIA, and the magnetic field will rotate and your springs will resist. And they get torque proportional to theta, and torque is proportional to Y. Now here there are two more important things. One is called current sensitivity. What is sensitivity? Sensitivity tells you, what is the smallest measurement that you can measure basically. It's like your least count. Sensitivity. We say sometimes, yeah, this person is very sensitive, even for small things, they feel bad. So it means what? Even for the smallest of the insult, you call him a monkey and they start feeling bad and crying. Yeah, this guy is so sensitive. There are some people who just don't care. So you're not sensitive. So this is NAB by I. Okay. This is theta by I, which is NAB by K. This is your current sensitivity. So simply it is an angle deflected per unit current. Think about this. Let's say I will deflect 1 degree for 1 milliampere. I will deflect 10 degrees, or let's say I'll deflect 1 degree for 10 milliamperes, which is a better instrument. So 1 degree is like 1 division, right? So you can see this more clearly, na? Means even if you deflect 3 milliamperes, the deflection is not even 1 degree, so you can't even see that properly. So higher the current sensitivity, more accurate the instrument is. It will have more decimals. So generally for instruments, you want it to be more sensitive. And that only created a problem, remember? Because it was so sensitive, if you send large current, they start burning up. That is the reason in ammeter and voltmeter, we have to keep a shunt resistance. And if you observe something here, if you want to increase the sensitivity, you can increase NAB. But the problem, if you want to increase B, you have to use stronger magnets. If I use stronger magnets, it might influence the nearby equipment. If I want to increase the area, the equipment becomes bigger. So one of the best ideas is to increase the number of turns. You can use a thin wire. If you use thin wire, you can put more turns. Right? NAB should increase. But if you use thin wire, you have more resistance. I square R, that means you can produce more heat, the wire will burn up easily. You're getting the problem. So it is like a sacrifice. You want it to be very sensitive, but if you try to send more current, it burns up. The second thing, this is an important question. They did ask few times, voltage sensitivity. This is your theta by voltage. So this is the voltage across the galvanometer. So voltage will be current into R. This is also resistance of the galvanometer. which is NAB by KR. So this resistance of the coil, which coil? This coil which I'm using here, which I'm winding up. If you remember the formula, it is rho L by area. It is proportional to the length of the wire. And the length is proportional to the number of turns. That means if you increase the number of turns, you're also increasing R. So N by R remains constant. So if you increase the number of turns, current voltage sensitivity won't increase. They'll ask us an important question. If you increase the number of turns, what happens? Current sensitivity increases, decreases, voltage sensitivity increases, decreases, voltage sensitivity does not change. I can frame options like that. So voltage sensitivity is, that means imagine if I apply 1 volt across the galvanometer and if it deflects 1 degree, right? And in the second case, if we double the number of turns, let's say I made the number of turns double. Then if I apply like, and let's say 1 ampere ke liye you got 1 degree, 1 volt ke liye you got 1 degree. If I double the number of turns, 2 amperes will give you 2 degrees, or 1 ampere will give you 2 degrees. 1 volt will still give you 1 degree. Get the catch? Simple reason, because you double the resistance, the current becomes half. So sensitivity will double, but the current has become half, so you go back to the old angle only. Voltage sensitivity is independent of number of turns. Clear with this? We had a big discussion on this.
Yes, sir.
This is the second most important thing. So first one was the vibrational magnetometer, next is moving coil galvanometer. Can we reduce K? You can mess up K also. You can, K should decrease. You can play with K also. All clear with this. The next thing. So these are the two main important things. And this is definitely important, even it's there for your boards. Next thing, tangent galvanometer. Now this is technically not there in the mains, but other exams they might ask. Not a difficult thing, so just see. What is a tangent galvanometer? It is useful to measure. It is used to measure BH. There. This is how the equipment looks. Pretty simple idea there. So you can see this thing. This is a circular coil. So when you send current through this coil will generate a magnetic field. And you adjust the coil such that the BH and the B coil are perpendicular. Then the needle will deflect along the net magnetic field. So if you look at this picture from the top view, this will be BH. This will be B coil. And what is B coil? B coil is nothing but number of turns. And the magnetic field due to circular turns is mu naught I by 2R. This would be the needle guide direction. This angle you will figure out from the experiment. Tan theta is BH by B coil. And the B coil, this whole thing will be a constant, mu naught N 2R, and ICA value, you can see how much ever current you send, accordingly angle will change. Normally this kind of experiments, what they do, first they'll send some current 1 ampere, they'll measure the angle, they'll send the second current, measure the angle, they'll divide them. So this constant goes off. You directly get that from there. Clear with this? That's it, there's nothing much here. Just have an idea. If they use the word tangent galvanometer, it should have a picture. Oh, yes, hoga. This is useful to measure the horizontal component of field everywhere. Because if you see, we keep saying the BH, 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 but how the hell do you find BH actually? You need to have a device to find that also. Clear with this. So this is about bar magnets. This is one part of the chapter. The second thing is magnetic materials. So this is also more theoretical, so listen carefully. Now, if you see materials, right, we have three types: diamagnetic, paramagnetic, and ferromagnetic. So how do we classify them and what exactly are these? So before even jumping into this, we need to see what makes a material into a magnet, atomic magnetism. So when you go at a molecular level, an electron going in a circular orbit is similar to a current loop. And we know a current loop will generate a magnetic field. That means each atom behaves like it's a magnet there. So current I will be E by time, which is 2 pi R by U, which is EU by 2 pi R. The magnetic moment mu is given by number of turns. N is this thing, I into area, which is EU by 2 pi R into pi R square. So we get mu is equal to EUR by 2. You can divide and multiply by mass, so this will become E by 2m into MUR. I hope you remember this thing. So we get a very important relation between them. Mu bar is equal to minus E by 2m into L bar. Mu bar is your magnetic moment. Minus E is the electron ka charge. If you remember the formula, it was Q by 2m. L was angular momentum. This is the relation between angular momentum and magnetic moment. Remember this? This thing was quite a powerful thing. If a solid sphere was rotating, hollow sphere was rotating, we can use this formula directly and finish it off without integration. This we did even in magnetic MEC. So that means when you say there is an electron going in a circle, and when it generates a magnetic moment mu bar, this guy is exactly similar to having a small bar magnet. So technically you can't tell the difference. So every electron that is revolving there produces a magnetic field. This we call as atomic magnetism. This is one of the most accepted theories so far, like why we get magnetism. Again, the fundamental question comes like, why does a current produce magnetic field? That we don't have an idea. So that is the problem with the science. At some point, you have to stop and say, we don't know. Then, now here, this is important for CET. This was asked. So from Bohr's theory, if you remember, first time when I heard this, even I was clueless what the hell they're talking. Then I had to search in the NCRT everywhere. There was one word somewhere. It's CET ka textbook mein tha actually. NCRT maybe tha, I guess. If you remember this formula, mu is equal to E by 2m into angular momentum. The formula becomes E by 2m into NH by 2 pi. So the magnetic moment is N into EH by 4 pi m. So if you take for N is equal to 1, the magnetic moment mu becomes E into H by 4 pi m. M is the mass of an electron. H is this thing. This is called as Bohr's magneton. This was the question. Which of the following is the Bohr's magneton? What is Bohr's magneton? It is the magnetic moment of the electron in the first orbit. If you remember that statement, it will be easy to derive even if you don't remember the exact result. It's a magnetic movement of electron in the first orbit. In the first orbit, what is momentum? H by 2 pi. What is a magnetic moment? Q by 2m into L bar. The terminology, right? Bohr's magneton, that was something new even for me a few years back. CET में तो direct question था वो. Then you can expect CET में questions do get repeated, and they ask 50 questions now, and the portion is 12 standard. The weightage becomes pretty high for these chapters. Straightforward question. The options were like EH by 4 pi m, 2 pi m, pi m, 2 is ऊपर. बस इतना था 4 options. They just played with that 2 ऊपर down and all, and it was confusing. So even though you know what is Bohr's magneton, if you just try to remember this result, there is a good chance you will mess up something. You'll write 4 in the numerator instead of denominator, or they'll put a 2 and you'll get confused. But clear what is Bohr's magneton? That is one part of it. Now, what are these diamagnetic materials? So, diamagnetic materials, again, an important question. What is the universal property all materials possess? Diamagnetism. All materials have some form of diamagnetism, and we will see what it is. It's called as universal property. What is the universal properties of the materials? Diamagnetism, paramagnetism, ferromagnetism, superconductivity is the 4 options. So what is diamagnetism exactly? Now, in a diamagnetic materials, all the electrons are paired up. Now you must have seen, right? When you read 1s2, 2s2, if you see, you keep the electrons like this, one arrow up and one arrow down, right? Normally you'll see this kind of pairing in lattices, copper, hydrogen, and all these things. So what do you mean by these arrows exactly? The meaning of these arrows is we have one electron going in one direction. So this will generate a magnetic field, mu bar. If another electron is going in the other direction, then the magnetic field is mu bar. And both the magnetic moments cancel out. That is the meaning of the 2 arrows. These arrows actually represent the magnetic moment. And because of this, the net moment, magnetic moment cancels off. So if you take a diamagnetic material and if you look at each atom, you will notice every atom is neutral. Basically, no one has magnetic properties. So mu of all atoms is 0. Therefore, mu net is 0. So if you just take a diamagnetic material, it does nothing. It does not exhibit any magnetism or anything. So these things, right? So you will see the true nature when you put them in an external magnetic field. So if you put an external magnetic field, when you place this in B external, what will happen? The B will suddenly, the field is gone from 0 to B. When the magnetic field suddenly goes from 0 to B, what will happen? No one remembers? They will generate an induced electric field. Whenever there's a changing magnetic field, you get an electric field. By Lenz's law, we get an opposing electric field. Which is circular in nature, induced electric field. And what will this electric field do? It will speed up one electron. The electron which is moving opposite to this field will start going faster because electron is a negative charge, force will be in the opposite direction. what happens to the other electron? And the other electron slows down. Since both the electrons are going at different speeds, what will happen? They will create a net magnetic moment. So they'll not cancel out anymore. This creates net magnetic moment. So when you take this diamagnetic material, these guys will start generating magnetic fields opposite to the B external. So normally they're neutral. But when you bring a B external, they start fighting back. And because of which they repel. That is how you can detect whether something is a diamagnetic material. They have a slight repulsion. B net will be B external minus B induced. You must have seen this kind of videos, remember? When you take a very super cooled conductor, a superconductors of magnets, you can even float a, frog. Ever seen this kind of videos? You put an apple floats on top of a magnetic field, frog floats on a magnetic field. Never seen this? I'll see if I can find a video, I'll send you. So normally when you take a superconductors, right, at very low temperatures, they generate very high magnetic fields. So even if you see, water is also diamagnetic. So when you take a frog or an apple, it has a lot of water. It gets repelled and it literally floats. I think the magnetic fields are around 8 to 10 Tesla. That's a huge magnetic field. Earth's magnetic field is 10 per minus 4 Tesla. When you go for an MRI scan, the magnetic field is 1 Tesla or 1.5 Tesla. 10 Tesla is huge. Diamagnetic materials repel. And because they repel, if they move from strong magnetic fields to weak magnetic fields. So the strong magnetic fields will repel with more force. They'll try to move away from there. And they'll go towards the weak magnetic fields. So they'll frame questions like this. They will say, if you take two magnets, north and south, and if you dump some diamagnetic material here, powder or something, and if you leave them for some time, or if you disturb them little, how will the shape form? Now understand, the magnetic field is strong near the poles. Center में it is little weak compared to the poles. And diamagnetic material gets repelled. So you will see this will actually start piling up in the middle. That is how the material will look like. Another very standard question, they will say as diamagnetic solution is placed in a U-shaped pipe. They'll say like this, a solution is placed in a U-shaped pipe. And when you bring a magnet close by, north-south, it is observed the left limb ka liquid level is lower, whereas the right limb ka level is higher. Then they'll ask, what kind of solution is this? Since the magnets repel, the liquid gets pushed down here. Therefore, this is a diamagnetic solution. Making sense? These are the kind of questions you get. So in a U-shaped tube, the liquid is poured inside and it is observed the limb where the magnet is placed, the liquid gets depressed. What kind of solution is this? Paramagnetic, ferromagnetic, diamagnetic, something of that sort. It's a diamagnetic. And if you try to draw the field lines, they do ask questions on this also. Which of the following is the field lines for diamagnetic? You can clearly see both the fields will oppose. That means the field lines will actually try to avoid this. They will try to go around it. So it's they're not happy with this material. They don't want to enter this. they will maximum try to avoid. So field lengths will actually decrease. Think about this. What is the number of field lengths per unit area? Magnetic field, right? So if the field is getting subtracted, that means the value is decreasing. Can you see how many points are there? The magnetic field length picture, the shape of the powder between magnets, liquid getting depressed. The story is important. There's still more some statements here. So if you remember mu r, which is nothing but relative permeability. For vacuum, mu r is equal to 1. So if you remember what is mu r, it tells you higher the mu r, more easily field can pass through. And for vacuum, it is 1. Means vacuum will neither support or resist. But your diamagnetic is resisting you. So mu r should be less than 1. This statement, remember, next class when I teach you EM waves, we're going to get a question based on this. For a diamagnetic material, mu relative lies between 1 and 0. And there is one more term here. So mu r is given by 1 plus psi. That symbol is called psi. It's actually called susceptibility. This was actually removed from the portion, susceptibility and all. But we are going to need this. So there is some graphs based on this in ferromagnetic and everything. So what does it do? It basically tells us how easily metal can be magnetized. And for diamagnetic, since mu r is less than 1, psi will be negative. Yeah, you guys are lucky actually. They removed a lot of nonsense things. It used to be a mess. There, that's about your diamagnetic materials. Clear this? Take a break, come back by 9:40. We'll continue from here. We got more theory. Sure, let's start off. Next thing, paramagnetic. So what are these paramagnetics? So in paramagnetic materials, right, we have unpaired electrons. That means now each atom will have a magnetic moment. So fundamentally, that is a difference. So when you look inside the material, you will notice even though each will have a magnetic moment, all these are completely randomly placed. There is no head and tail. So mu of the atom is not zero, but mu net is zero. That means if I give you diamagnetic powder and paramagnetic powder, you can't tell the difference. They will look same. The difference is fundamentally when you get a molecular level, then you see the difference. At a macro level, they will look identical. Since all magnetic dipoles are randomly placed, mu net becomes zero. And if you apply B external, now what will happen? All these dipoles will start aligning. Torque is equal to mu cross B. This is how your picture will look. B net becomes B external plus B induced. So field actually increases. And if you try to look at the field length of picture, there have been questions like this also. They'll ask which of the following is a diagram for paramagnetic materials. So this thing, right, they will actually get pulled in. So the lines which are closer, they will just try to get closer to this. B increases. So if you see now, paramagnetic materials have weak attraction. And they move towards strong magnetic fields. Because since they get attracted, they will go towards the strong magnetic fields. See, when you're getting repelled, the strong fields will push you away. When you're attracting, strong fields will pull you towards them. So now if they ask you that question again, the magnets, committal and stuff, the red diagrams for B net, this left one, yeah, the left is B net. This is how the material will be. Near the poles, there will be more material. Near at the center, the material will be less because near the poles, the field is stronger. So it gets attracted towards the strong. This in middle may is weak. So the shape will be like this. And the same story, if you take a U-shaped pipe and if you fill it with a paramagnetic liquid, and if you put a magnet, so here the liquid will rise. On the other side, the liquid will be less because of attraction. Then we have something called Curie's temperature. Curie's law. Now, what this law says is this size, susceptibility, if you remember, is 1 by temperature. Again, what is susceptibility? 1 plus susceptibility is mu. And what does mu tell you? Mu tells you how easily field can pass through. Now, what happens here? Think about this. If I increase the temperature, the molecules will start vibrating. If the molecules start vibrating, then all of the molecules will not align in the same direction. That means higher the temperature, there is a higher chance the magnet will lose its property. So that is one other thing. If you take a magnet and start heating it, it will lose its magnetic property. It will stop attracting. So the molecular vibrations will mess up the poles. They start becoming random. So even though the external field is trying to put you in same direction, the temperature will make you vibrate and mess up things. Increase and they do not align anymore. It's like imagine, right? When you join people in an army, right, they become disciplined. But if you take 100 mad people and put them in the army, it doesn't matter. That's something of that sort. When you have high temperature, molecules don't listen to you anymore. So, and when you plot the susceptibility versus temperature graph, you can clearly see it's a rectangular hyperbola. There. So susceptibility technically is removed from the portion, but it is there in Curie's law in paramagnetism. And this is what they have done. It's like saying, we removed loss of motion, but friction chapter is there in exams. And that is how it looks. It's a cruel joke, basically. People are happy. Oh, NLM is removed, but friction is there. It's like, what the hell? Kinematics 1D is removed, projectile is there. Next thing, ferromagnetic. These are some of the most tiring chapters. Right? Normally, every other chapter, right? I used to give you questions you guys used to do. I used to listen. Now you guys are listening. I'm talking nonstop. So, what are these ferromagnetic things? So, the difference here is this ferromagnetic, right, has something called domains. In each domain, all the poles are aligned in the same direction. So, these regions are called domains. So if you see in diamagnetic, each molecule was zero. In paramagnetic, each molecule had dipole movement, but net was zero because they cancelled out. In case of a domain, each region has a very strong magnetic field, but all these regions are random. So these regions where all the dipoles are in the same direction is called a domain. And these domains are randomly placed. Therefore, mu net is 0. So all the three materials, the net magnetic moment is 0. If you don't apply any external magnetic field, you can't tell the difference. Only when you put the external magnetic field, then you will see they'll act differently. So ferromagnetism, right? It does exactly same thing whatever paramagnetism does, but it does strongly. It is like, paramagnetism on steroids. Something of like that. It's like paramagnetism is a bodybuilder. Ferromagnetism is Hulk. So to put it in simple words, think of like this. Cat and a lion both belong to the cat family only. Ferromagnetism is a lion, paramagnetic is a cat. So ferromagnetism is a stronger. So all the properties you said for para will work here. Right? If you look at for para, so mu r will be, let's say, 3 or 4. For ferro, if you look at mu ion, it's 4,000. Getting it? This will be like single digits. For para, mu r will be something like 3, 4, 5, something in that range. So I'll just not write that because it can be 10, 15 also. But this will be huge. Mu r will be much, much greater than 1. So if you try to look at the magnet, this guy is so strong, it will literally pull every line that is there in the region through this. It will be pretty concentrated. The feelings will completely try to get, absorbed by this thing. And here we define psi, susceptibility is given by, it's a constant by T minus Tc. Something happens here. If you keep increasing the temperature, these domains will get destroyed and they become like paramagnetic. So this Tc is called Curie's temperature. This is the temperature at which ferromagnetic becomes paramagnetic. Materials which are aligned in dipole domains is called ferromagnetic. They're actually pretty close to, generally, ferromagnetic meaning, if you see this iron and all these kind of materials, right, they're pretty close to magnetism. So when you want to make a magnet, that's the reason they use iron and all that stuff.
But like, why don't they stay like paramagnetic materials?
You need to go and read more theory, then we don't have all that explanation, so don't worry. I understand your point. So if you want an explanation, it will be something like this. Let's say once this thing forms a small magnet, this will start attracting the nearby things, but they can't completely align, so they will just become normal and stay back. You will get some theory like that. Clear with this? That is about ferro. These are the three materials. That's about magnetism. Clear with this? So in this whole chapter, the important thing is the vibrational magnetometer, then moving coil galvanometer, right? And para ferro, this thing, if you ask me in this again, especially these questions, this one, these are important. The pictures, that one, the diamagnetic is a universal property, right? Diamagnetic a value mu r is less than 1. Yeah, again, these pictures and Curie's temperature. Again, if you see just today only, I must have introduced at least 10 new terms. Terminology is the key, everyone, because if you understand what is the meaning of this, most of them you'll get the questions. The biggest problem I see people now, they don't remember the terminology. Someone will come and say susceptibility, and they're like, what? Curie is temperature. Then you will think about, radiation ka, the Madame Curie thing. Because 1 unit of Curie, yeah, that 10 power minus 10 disintegrations per second, that's 3.7 something. So you'll start mixing up stuff. So you have to be careful. That's about your magnetism. Next thing, optical instruments. This is a part of, again, ray optics, but again, therefore means. So listen to this thing. Again, not tough. We have microscope, telescope. Those are the two main things. Before TC, 1 by X is not defined only. It becomes paramagnetic. No? It is not ferromagnetic anymore. So we don't define. If the temperature is less than critical temperature, we don't define it only. The graph basically stops. You're asking this, no? The graph is not defined only. Because it's a graph for ferromagnetic materials, but the material has become paramagnetic. Now, what are these optical instruments exactly? Now, again, if you blindly remember the formulas without understanding why you got it, you won't be able to remember them or derive them. So technically speaking, I would always suggest you should know how to derive them, because exam there's a good chance you'll forget something. So let's see, what is this? So the whole story starts like this. When you look at something, what are you actually looking at? This we talked in circular motion. When you see an object, are you actually looking into the length of the object? If you are looking at the length of the object, right, that means if you think of like this, take your finger and put it in front of your eye and look at the computer screen in front of you. Which looks bigger, the finger or the computer screen? The finger, right? So if your eye is measuring length, why all that? If you take a finger and see the building in front of your house, your finger will look bigger than the building. We know the building length is longer. We know, getting it? We know. That is because we using our head. But if you just, if you are a creature without any, thinking power, you will definitely think your finger is bigger than the building. And that's what animals do. Getting it? They can't think, they don't realize. So what you're actually looking at is not lengths, we are looking at angles. We are angular creatures. When you look at an object, you look at angular velocity. When you look at an object, you look at angle subtended by it. Right? So human eyes and cameras. See the angle subtended by the object. That is the first thing you need to know about the eye. So if you have a tree here, which is 10 meters, and let's say this is a distance of 100 meters. This angle be theta 1. So tan theta 1 is 1 by 10, approximate to theta 1. Let's say another object is 20 meters, but you're looking this from 500 meters. Here tan theta 2 is 1 by 25. So you can clearly see, since theta 1 is greater than theta 2, the 10 meter looks bigger than 20 meters. There. That means if you want to see something, you want to see big angle. You're getting it. It doesn't matter how big the object is. If the angle subtended is small, you can't see it. Now we human eyes, right? We have a sensitivity of around 0.6 minutes. 60 minutes is 1 degree. Our eyes are very, very sensitive. Matlab, you can actually literally see an angle of 0.6 minutes, and 60 minutes is 1 degree. Matlab, socha how small is that? So if 2 points subtend such a small angle, you can actually differentiate there are 2 points. You're getting it? It's something like For example, say, if I just zoom in, these are 2 points. You can see them. Can you still see them? There are 2 points. Now it looks like a point, right? Do you know where is the point? Let me zoom in. अभी दिख रहा है point? Did you find the point? This is a game, finding the point. I'll zoom in. See, now you'll be able to see the point. अभी दिख रहा है point कहाँ पे है? Now can you see? You can see there are 2 dots. You can see a slight gap between them. Now you can definitely see there are 2 points. Now if I zoom in, observe that point. Can you still see there are like 2 points? Some of us can see, some of us can't see. It happens. I can see there are still 2 points. But once you go beyond something, then now it is gone actually. There's a single, just looks like one thing. So you can't differentiate. The angle subtended is too small. So the best thing is this: stretch your hand and look at your fingerprints. Put your hand far and look at your fingerprints. Can you see your fingerprints? Just stretch your hand maximum, okay? And then try to look at the fingerprints. Can you see? You can't see. Generally, you can't see. If you can see, have some super eyes. Now get it closer. Get it closer. Get it closer. At some point, you can see your fingerprints. Once you bring a certain close enough, you can start seeing your fingerprints. Did you start seeing your fingerprints? Now get it even more closer. Now the fingerprints will be more clear. You can see more fingerprints. Still get it closer. More clear. Get it closer. You can't see anything. Did you observe something? If you bring it too close, you can't see it anymore. Your eyes actually will start, getting irritated. Try to look at your nose. Don't try too much. You'll get a headache. You can't see clearly, right? It throws you off the focus. It feels pretty weird. There is something there, but you can't see. It looks like a frog or something. Right? It doesn't look like your nose anymore. So our eyes have another problem: distance of least vision. So see, one thing is clear. You want to see something clear, you have to get a big angle. How to get a big angle? Get the object closer. But if you get the object too close, you can't see. This is called a distance of least vision. Capital D. So the minimum distance up to which you can focus on the object. For kids, this will be around 8 to 10 centimeters. For adults, it goes up to 25 centimeters. As you get old, it can even become 1 to 2 meters. That's if you see old people use reading glasses to read. They can't put the book close and read. Up to which our eyes can. That is the reason you can't see your nose. Because it is less than this distance of least vision, it throws you out of the focus. If you try too much, your eyes will actually get strained and you'll get a headache. Generally, this value turns to be 25 centimeters. If they don't give anything, take 25 centimeters. Clear with this? There. Now we have two contradictory things. Matlab, you want to see something, you need to get it closer. If you get it too closer, you can't see. Right? So, ठीक है ना, use your fingerprints. Aditya. That doesn't depend on screen resolution. So now here we define theta naught, which is h by capital D. So this theta naught is the maximum angle you can see without an instrument. So when you put something at the distance of least vision, it gives you the maximum angle. Maximum strain, but this is the maximum angle you can see with your eye. Again, we're assuming all these angles are small, so we'll always write tan theta is theta only. This angle is theta naught. There, till now we have two terminologies, capital D, distance of least vision, and theta naught. And we define angular magnification. So when you use optical instruments, the magnification is studied in terms of angles. So this angular magnification M is given by theta naught, where theta is angle with instrument by angle without instrument. Now let's see our first device, simple microscope. Listen carefully. The idea is important. Matlab, these things can be framed even in advance also, because it is all ray optics only. Your lens formulas and everything. So what is a simple microscope? A biconvex lens. If you take a simple biconvex lens, it can be used as a simple microscope. Now listen to the idea here. So you take a lens, focal length f. Now again, what is the story? In order to see the object clearer, you need big angle. For big angle, you need to keep it close. So you went and kept it close. The moment you did this, the distance became less than capital D. Your vision went away. ठीक है, इतना तक story था. So what we do, we keep a lens, and this will be your pole, and this will be the focus. So we keep the object. These are the theoretical questions. So object is placed between focus and pole. So you tell me, in a lens, if you put this object between focus and pole, what kind of image you get? This guy will form an image which is virtual, erect, and magnified. Isn't it? I hope you guys remember. Great. So actually, if you look at the light rays here, the light ray which is going through the pole will go undeviated. So it feels like it is coming from here. This is the angle subtended. Did the angle change actually? So this distance is V. So from here you can clearly see theta is nothing but height of the image by V. This is h by u. So by keeping a simple microscope, did the angle change? Height of the image increased, but distance also increased. Angle remained same. But did you notice something else? The distance increased. That means the distance became greater than capital D. Na? Now suddenly it is in your vision ka range. So this is what I did. See, if you're looking into my screen now, I want to see my fingerprints. I kept it this close. I can't see. By keeping it close, what did I do? I increased the angle, but I can't see. Now, where I took a lens and kept it between the object and my eyes. When I kept the lens here, what happened? The image formed far with the same angle, the bigger angle. Now what I'm looking through the lens is not the object anymore, but the virtual image, which is at a distance greater than capital D. Now I can see the image, right? I increased the angle by keeping it close. But the drawback, the distance became too close. By keeping the lens, I didn't increase the angle, but I increased the distance. Now I can see that thing. Are you getting how this thing work? So because you kept it close, you increase the angle, and the microscope will increase the distance of the image so that it will be in your vision ka range. So the magnification M is given by theta naught. So theta is h by u and theta naught is h by d. So magnification of a simple microscope is d by u, where d is the distance of least vision and u is the point where you keep the object. But remember, it must be placed between focus and pole. Now here we have two cases. Generally, when they ask magnification, they'll ask you these two cases. The first case is your normal adjustment. They'll directly ask you this. What is the magnification of a simple microscope in normal adjustment or far point? So the meaning of far point is the image which forms is at infinity. Now, when you're working in front of a computer, normally this software people, normally they have a rule called 20-20-20. What it says is, if you're working in front of a screen for a long time, for every 20 minutes you watch the screen, right? Look something which is 20 feet far for 20 seconds. The idea of this thing is your eyes, na, when you're looking at something close, your muscles actually get compressed and everything, they're stressed out. Next time, observe this. When you go out and look into the sky, your eyes feel actually very relaxed, normal. The reason is this: your eyeball is there, the retina is there, retina is exactly at the focal length. When your eye is completely relaxed, the focal length of the eyeball is the retina. So when the light rays are coming from infinity, they directly form at the retina, you can see the image. That means you can keep staring into the sky for hours and your eyes will be like pretty good. But if you keep watching the screen for 1 hour or 2 hours, you will actually feel like your eyes are exhausted. Right? So now you tell me, tomorrow, let's say some person is working on, this looking at this bacteria and everything, and they have to keep looking through the microscope for 2-3 hours. So now what we are doing is, if we can form that image such that it is at the focus, the letters will become parallel. That means you can look through the microscope for as long as you want and your eyes will be completely fine. Is that making sense? So final rays are parallel. So this is where you want to operate your microscope. Next time when you see any movie and all, no, observe this thing. The hero or the heroine will put something there and will try to keep adjusting the microscope. What you're trying to do is this. So if you want the final rate is at infinity, object is at focus. So U will become F. So the magnification is D by F. There. That's your result. What is the magnification of simple microscope in normal adjustment? D by F. D is 25, F will be given. There is a direct question like this. They said focal length of a lens is 5 centimeters. Find the magnification of simple microscope in normal adjustment. Now it looks easy, but exam mein socho, look at the words in that. Find the magnification of simple microscope. There your fuse must have gone. Simple microscope, you heard the word, but you don't remember anything. Right? And the magnification in normal adjustment. That is the second fuse blows off. What is normal adjustment? Third, magnification, what is the formula? That is the third fuse blows off. Formula D by F. What the hell is D? I think if you actually the first three fuses are still safe, I hope you'll remember capital D ka value. Getting it? Questions won't be tough. The terminologies. Case 2, near point. What if the image forms at capital D? That means the image which is forming there is on the boundary of your vision. That means your eyes will be maximum strained. Image forms at distance of least vision. Now, these things are important. Means they might not touch, but advanced they can play around because it is justly again ray optics only. Lens formula 1 by V minus 1 by U is 1 by F. So 1 by V is 1 minus D minus 1 by U is 1 by F. Magnification, we know D by capital U. So divided by D by U, you will end up with minus 1 by minus 1 plus D by F. There. So in near point, you get magnification 1 plus D by F. You actually get slightly more magnification, 1 unit more. But your eyes are maximum strained. Not worth it. So the magnification of a simple microscope will lie between 1 plus D by F and D by F. Depending on what case you're taking, these are the two extremes. Clear with this? Now, how will they frame a question on this? Every time you won't be so lucky, they'll ask a question directly like this. A biconvex lens of focal length 20 centimeters is used as reading glasses by a person. Capital D is 25 centimeters. Find the closest and the farthest distance a book can be placed so that it can be read with the glasses. So there's a person there whose distance of least vision is 25 centimeters, and you have this magnifying glass, focal length 20 centimeters. Find the closest and the farthest distance. So you're trying to read a book through this lens. So what is the farthest and the closest you can keep this book at which he can read the book? Let's see how will you approach this. Listen, don't worry about the book and all. Do the reverse. You tell me, can you see if, as a person, can you see something very far? You can see the stars in the night, right? You can see stars in the night. That means you can see something which is at infinity. And what is the closest you can see? Capital D. That means you can see anything from capital D to infinity. That means this book is the object. The lens is there. So the image formed by the lens must be between infinity and capital D. Think like that. You are capable of looking at any image which is from infinity to capital D. Image can be between infinity and capital D. So using that as a logic, so for the image to be at infinity, object should be at the focus. That is 20 centimeters. So that is one extreme limit. The second extreme is when the image forms at capital D. That is V is minus 25 centimeters. So using the lens maker formula, 1 by V, 1 by U is 1 by F. This comes out to be minus 100 by 9 centimeters. That means when you keep the object at 100 by 9, the image will form at 25. When you keep the object at focal length, you can see the image at infinity. That means the book can be placed anywhere between 20 centimeters and 100 by 9 centimeters. Make sense? That is how you handle these kind of questions. You go in the reverse, you see start from the image. Yeah, got it. There, but the simple microscopes have a problem. Once the magnification exceeds 4, they start actually getting aberrations. They start creating all kind of errors, which we'll see later on. When you put a lens, right, there is something called a chromatic aberration. So using one lens for more and more magnification is a problem. So we go with compound microscope. We use multiple lenses. So in a compound microscope, we use two lenses. We can use more, but we are saying for two. The one is called eyepiece because it's closer to the observer. The other one is called objective piece because it is closer to the object. The idea is pretty simple. If you understand the idea, right, it will be easy to solve. So we have the object here. So first the objective, what will it do? The objective will create a a magnified image. And this magnified image, you try to look at the eyepiece. You're getting it? That means this has become simply a simple microscope. Na? Eyepiece is a simple microscope. The objective piece will make the image bigger, and that image you look through a simple microscope. So it is a combination of a lens plus a simple microscope. Are you getting it? So first you make the image bigger using one lens, and that big image you look through the eyepiece. This focal length is f naught, and this focal length is fe. Now listen to the derivation. This derivation is not there in NCERT. They gave something else. They gave the final result, some weird result. That is what we'll use for mains. But in these questions, right, I feel they can even put it in a paragraph, because it's all based on Lenska formula only. Yeah. So what we do, we magnify the object through the objective piece. Then see the image through the eyepiece. This is your simple microscope. Then, so the total magnifying power will be the linear magnification of objective understand the objective will create a real image and the eyepiece will create a virtual image. You can actually make the object also create a virtual, nothing wrong, but yeah. Into angular magnification of eyepiece. What is the linear magnification का formula? VE by UE. What is the angular magnification? Sorry, V naught by U naught. Image distance by object distance. Angular magnification is D by UE. How did I get that? Remember the formula for simple microscope, D by U. So your regular magnification is V naught by U naught, and your angular magnification is D by UV. So when you combine this, you get, again in this, we have two cases, the normal adjustment or the near point. This is what is given in NCERT as a direct formula though. Whenever you hear the word normal adjustment, near point, meaning the final image or the final letters have become parallel. From there, if you go behind, so this is the object, this is the image. Since the final letters are parallel, this must be the focal length Fe. The letters have become parallel. That means this is VE, this is UV. So using the lens maker formula there, and this is UV. 1 by V by, sorry, this is V naught. 1 by V naught by 1 by U naught is 1 by F naught. Magnification of object F is V naught by U naught. If you multiply V naught on both the sides, you end up with V naught by F naught minus 1. Magnification of eyepiece, d by UE, which is d by FE. Therefore, the total magnification is V naught by F naught minus 1 into d by FE. This is your actual formula. Far point, sorry. Magnetism is far point. It was a mistake. And we also define something called length of the microscope, which is V naught plus FE. What is the length of microscope? The distance between the two lenses. These are your main things. That's what I'm saying. It is difficult to remember this. If you know the process, you can derive them in 1 or 2 minutes. If at all they mess up something in the question, you can handle this. But what they gave in NCERT was something else. So listen what they gave. Now we know the magnification is V naught. And it's not like every time they'll make it complex also. Most of them, the questions are easy. This is one of the easiest questions they asked. The question was this. In a compound microscope, for more magnification, which of the following statements is true? F naught is big, Fe is big. F naught is small, Fe is small. F naught is big, Fe is small. F naught is small and Fe is big. ऐसे 4 options था. This was a straightforward question. People got confused. Because in telescope, the answer will be different. We'll see later on. You can clearly see both are in the denominator. So if you want more magnification, both are small. This was a question in the exam mains. This is an important one. Now what NCERT did, because F naught is small, V naught by F naught minus 1 is approximately V naught by F naught. Since F naught is small. And we know length is equal to V naught plus Fe. This is also approximate to V naught because Fe is small. And then the formula became magnification LV naught has become L by F naught D by Fe. There, this is the formula which is given in NCERT. So exam, there have been questions like that. They gave L ka value, F naught and Fe ka value, and they asked for magnification. So this is a compound microscope for normal adjustment. Mostly mains, I don't think they'll go beyond this formula unless they decided to slaughter you guys. And advancement, they can make this as a paragraph. Because if you see, it's all about lenses only. They'll explain you what is magnification and they'll ask you the question. So do not underestimate this. That's your near point there, far point. Now the near point is not that important, but let's see. Again, what is near point? Image is at capital D. So if you know that much, it is sufficient. Then it is just lens ka formula only. Image is at capital D. So draw a picture. You will see everything. So your object, you get the image. When you extend them, the light rays are meeting somewhere here. This is capital D. This is V, U naught. This is V naught. This is UE. This green one is your final image. That's it. If you know this picture, you're done. You have to apply the lens formula 2 times. So 1 by minus d by 1 by minus ue is equal to 1 by fe. So d by ue will be d by fe plus 1. So total magnification will be v naught by u naught into d by ue. In this case, they'll give you the value of u naught. From there, you can find v naught and substitute here. There, this is your magnification, and length will be v naught plus uv. There, if it is not normal adjustment, then they'll give you some data points. Then you have to solve. Clear with this. So this is about the simple microscope and compound microscope. Then we have something called telescope, which we'll see in the next class. That's actually more easier than the microscopes. And yeah, that's it. Then we have telescope and it will be done. We will see some more few examples. I think we'll take another 15-20 minutes. We'll wrap it up. So next class, when we catch up on Friday, we'll continue with this. We will finish off optical instruments like a small thing. And like I said, whatever is left, it's all small topics. We'll finish off like two things every class. The next class will start off with EM waves and polarization. That's an important thing. You get a lot of questions from that. So we will do electromagnetic waves and polarization on Friday. After that, we'll be left out with diffraction and dispersion and Bernoulli calipers and screw gauge. We will finish up aram se by next week. Okay, with that we'll wrap up for that day. So I'll see you guys again on Friday. So make sure to finish your magnetism is also done now. So start doing PYQs, don't delay, don't wait too long, you'll forget all this stuff. So make sure to go through what we did today. Finish your semiconductors ka PYQs. Again, I told you last time. If you think you can't do everything,